Good afternoon, everyone. My name is Tristan Caetano, and I am joined by my Scrum Master, Jacob Holme, and today we will be presenting our project, the Network Traffic Alert Notification Pipeline, which has been given to us by our client, Benjamin Drozdenko, from the Naval Undersea Warfare Center. I will now be passing the presentation off to Jacob so that he may introduce it.
So first, I'd like to get into our project requirements. So we had to protect the confidentiality and the integrity of data on an internal network enclave that was not connected to the internet. So we had to do this by creating a system to recognize the presence of malicious network activity by zero-day exploits and insider threats. We had to develop an AI machine learning algorithm to monitor network traffic, which would classify groups of packets as either malicious or normal, and notify the LAN admin of malicious activity. The LAN admin needed to be able to react to this information without being presented any unnecessary information. A simple GUI was requested so that the LAN admin could see alerts and modify the pipeline's parameters and settings. So with these requirements in mind, I'd like to discuss the elements of this project. So our project is split up into four main parts: the GUI, data conversion, data organization, and the algorithm. The GUI, as I said previously, provides user access to the program's functions and allows them to modify different parameters. The data conversion converts network data from a PCAP file into a readable file for our algorithm, which is a CSV. The data is organized by being parameterized, normalized, and created input sets. These input sets are sent to the algorithm to determine if the packet is malicious or not. So our project is split up into two main pipelines. We have the main pipeline and the Retrain Algorithm pipeline. Our main pipeline inputs a PCAP file, converts it to a CSV, parameterizes it, normalizes it, and sends it to our algorithm. Our algorithm creates a predicted CSV and outputs that to the GUI for our LAN admin. Our Retrain Algorithm pipeline inputs a CSV dataset and creates a train CSV, a validation CSV, and a testing CSV. These three CSV files are then parameterized, normalized, and sent to our algorithm. Our algorithm uses these three files to create a model file, which we can later use to analyze more data without having to retrain it. Next, I'd like to get into the development of our project. So let's start with our GUI. GUI has two menus, as you see here. It has the main pipeline and the Retrain Algorithm pipeline. And the main function of our GUI is to just display the process CSV files and system outputs in a clear, organized way. Next, I'd like to discuss the PCAP to CSV converter. So what is a PCAP file? You can see a PCAP file pictured here on the slide. It's a file that contains packet data of a network, and we use these packet data to analyze network traffic and activity. So we can see the PCAP pictured here on the right again. Each color-coded row is an individual packet, and each packet contains the information shown in white, which is difficult to read in this format, which is a big reason why we had to convert it. So what does the conversion look like, and why do we need to do it? So this is the PCAP file after it's been converted into a CSV format. It's easier to parse and manipulate data in Python this way. It allows us to organize, normalize, and manipulate the specific cells using Python libraries, pandas, sklearn, and XLW2, and it made it overall easier for us to read. The function of the converter. So on the right, we have a PCAP file, a CSV displayed in text format, and a CSV displayed in cell format. The converter inputs a PCAP file, it converts it and outputs the CSV text format. We use display filters in T#, which is a terminal-oriented version of Wireshark, to filter through these important values and send them to the algorithm. Next, I'd like to hand things back over to Tristan so he can discuss the data parameterization, normalization, and training set creation.
Next slide, please. Before I actually get into these aspects of the project, I would firstly like to discuss the data sets that we use to actually do the training of our algorithm. The data set that we used is from the University of New South Wales, and it's actually 4 separate data sets that combined create about 2.5 million packets. In each of these packets, there's 49 columns worth of features, and we can see column 48 and column 49 over on the left-hand side. Column 48 is actually a string that contains the name of the malicious packet type, and column 49 is a binary value, 1 or 0, basically saying whether or not the packet itself is malicious. We can see this representation over on the left-hand side. On the top left, we have a blank cell, which represents a clean packet, and the bottom two cells, exploits and DOS, are basically the strings representing what the actual types of malicious packets are. Over on column 49, we actually have a binary value, as I said previously, on the top right, we have a 0 indicating that that packet is clean. And over on the bottom, we have 2 ones indicating that those 2 packets are malicious. There are actually 10 different types of packets. However, 4 of them didn't have enough instances in the 2.5 million packet data set to warrant trying to get our algorithm to learn about it. Next is the training set creator. We actually have 3 different data sets. We have a testing, training, and validation set. The training set is about 64% of the allocated packets. The testing set is 20%, and the validation set is the remaining 16%. Each of these packet types are evenly divided within each CSV file, and there's a 5-to-1 malicious to clean ratio. The reasoning that we have this is the algorithm, we want the algorithm to be biased more towards malicious packets. And once these data sets are created, they are then sent to the algorithm so that it may learn to recognize these malicious packets. Next, we have the data parameterization. As I said previously, in column 48, a lot of these malicious packets, especially the ones that are the malicious packets, have different types of names. And these names actually need to be converted into integers, so they need to be processed through our machine learning algorithm. And that's what parameterization does. So for example, let's say we assign the clean packet or the blank cell to be a 0, exploits as a 1, and so on and so forth. Once this data is properly prepared and the AI algorithm is sufficiently trained, it can be fed through the algorithm for testing, which is what the testing set is for, and I'll get into that in a little bit. The process itself is performed on both the training sets and the converted sets in both of the pipelines. Next, we have data normalization. And this is the next step in the data preparation for the actual machine learning algorithm. Firstly, we can see this representation. It's a very simple example over on the right-hand side, where we have a very basic version of data normalization. The exact version of normalization that we used is called Max Normalization. And we can see this once again. On the left-hand side is the original column, and on the right-hand side is that data normalized version of that column. And although this is, once again, a simple representation of data normalization, we can understand how this can be upscaled to a much larger data set that we're using. On the left-hand side, we have values 1 through 6. What min-max normalization does is it takes the minimum value, so in this case 1, converts it to a 0, takes the maximum value, which in this case is 6, and converts it to a 1. Every value between those 2 values are then scaled accordingly, and this is effectively what normalization does. The reason that we do this to our data set is so it actually makes the machine learning algorithm train faster and more efficiently. And finally, we have the multi-class and binary classification algorithms themselves. So first, I would like to get into the goals of the algorithms. We are actually using 2 separate algorithms that can be chosen by the user. We have the binary algorithm, which, as its name entails, is a binary value between 0 and 1 for determining whether or not a packet is malicious. And we also have the multi-class classification, which is multiple different values for our feature set. As I said previously, it's a 5-to-1 ratio, so there's 6 different types of packets, one of which being the benign packet, and then we have the 5 different types of malicious packets, which include exploits, reconnaissance, DOS, generics, and fuzzers. The asymmetric data, because of that 5-to-1 ratio, will actually cause the algorithm to lean more towards malicious data, which will result in false positives rather than false negatives. And we can see why this is important in a security type situation where, let's say if we have a clean packet that's accidentally flagged as malicious and not allowed into the network, that's a lot safer than having a malicious packet which is accidentally classified as clean and allowed into the network. And of course, before we can actually use the model to train our converted set, we have to train the model itself. So once again, we have the training, validation, and testing sets. The training set itself is used to train the model. The validation set is used alongside the training set to adjust the parameters between epochs. An epoch is effectively a machine learning algorithm going one complete pass through the entire data set that we provided. And the testing set is actually used after the model is trained to make sure that the predictions are reliable after the training is completed. The algorithm itself, the goal of it and what it does is it effectively tries to look for correlations between the packet information and the malicious packet type, and it's trying to find those correlations so it can effectively predict what the packet is based on various features. And of course, once the training is completed, the model is then saved to a file, as Jacob spoke about earlier, and it can be used to make predictions on the PCAP to CSV converted set, which is our main pipeline. We can see the training visualized over here on the bottom. We have the training CSV and the validation CSV being sent into the AI algorithm for training. This AI algorithm then outputs a model file, which is then sent back into the model with the testing CSV so that we can actually observe the predictions that are made by the model. And the reason that this is important is the testing CSV, we actually already know in the testing CSV not only whether or not each of the packets are malicious, but what type of malicious packet it is. So we can compare our predictions to what the actual types of packets are. While creating this algorithm, we learned a lot of different attributes. Firstly, that accuracy is not a good standalone metric for determining how good our machine learning algorithm is. Effectively, it only represents the percentage of correctly predicted data points. Other metrics that would have been better to use to kind of validate our machine learning algorithm would be precision and recall. Precision being how many positive predictions are correct, and recall being how many positive predictions were made out of all of the possible positive predictions. We changed multiple different attributes of the machine learning algorithm to achieve the optimal results, including the learning rate, layers, neurons, activation functions, and optimizers to see if we can get the best possible results from our predictions. And finally, I would like to show you our loss functions for both of our algorithms. So both of these loss functions actually use the same exact data set, and this is our transformation of our loss over about 50 epochs. And effectively what the loss shows is it shows the difference between the expected outcome and the predicted outcome, and as evidently shown, the lower the value, the better the performance of the algorithm. I would like to show you now our demo. Can everyone see clearly? So this is our GUI as we spoke about previously. And what we're going to do is we're going to be creating our training sets. We're going to be training the algorithm. And finally, we're going to be running our main pipeline. Firstly, I'm going to have you click on the settings menu. We're going to click on create training data. And we can actually see that we're training a multi-class algorithm here. If you can click on the CSV. And then we're going to do about 1,000 packets. Normally, in a real-life type situation, you would want to use much more packets to have the largest data set possible to get the best training out of your algorithm. But in this case, for demonstration, we're just going to do about 1,000. Okay? And we're going to put in 5, and this is effectively asking for the index of a column that contains all of this malicious packet information. And right now what's happening is through our original UNSW data set, the training test grader is effectively going through grabbing as many packets as it can, or how many that we asked it to, and creating 3 different data sets, testing, training, and validation. So now it's completed, and we can actually train our algorithm now. If you want to click on Retrain Algorithm, we can select firstly our training data. And these are actually the normalized versions of our data as we spoke about previously. Next, our testing data. And finally, the validation data. And now we can name our HDF5, or what the model file is. We can name it anything. In this case, let's just name it new. Now what's happening is our machine learning algorithm is going through our training set, and every epoch it's going through the entire training set, trying to make correlations between the actual packet information and the type of malicious packet itself, and then using the validation set to make sure that its predictions is good in between, and the loss function is hopefully decreasing between each epoch. Now that the model has been created, we need to import the model. Select new.h5, and our model is successfully imported. We can X out of this menu, and we can now choose our PCAP file. In this case, we have split.pcap, which is a small PCAP file used specifically for this demonstration. And we can click Start. Now what's happening is our machine learning algorithm, firstly, we're actually converting the PCAP file to a CSV file so that it can be read by the machine learning algorithm. We're then parameterizing that information, normalizing it, sending it to the AI algorithm, and now we're spitting out all of the PCAP information into a CSV format that is seen on the screen here. If you scroll all the way to the right, we can actually see the predictions all the way on the right-hand side. And as we can see, our machine learning algorithm believes that all of these packets are clean. If you'd like to go back to the presentation. That is our presentation.